There is a moon in our solar system where the ground is actively melting, where volcanoes erupt not with rock, but with liquid sulfur, and where the surface is being completely replaced so fast that craters formed millions of years ago no longer exist. There is another one hiding an ocean beneath its ice, a liquid ocean that has been sitting there longer than complex life has existed on Earth. One moon orbits its planet in the wrong direction entirely, moving against everything around it, a sign that it does not belong where it is and never did. Another has cliffs that drop 12 miles straight down. At that moon's gravity, a single misstep off the edge means 11 minutes of falling before you hit anything. These are not distant hypotheticals. These are real places, photographed, measured, mapped. Some of them have been visited by spacecraft. Some have barely been looked at. All of them are stranger than the word moon suggests. When most people hear that word, they picture the pale disk overhead, the thing that pulls the tides, the thing that has been there every night their whole lives. That image barely scratches what is out there. Across this solar system, orbiting Jupiter and Saturn and Neptune and Uranus and Mars and even Pluto, there are worlds that have weather systems, active geology, subsurface oceans, organic chemistry, geysers erupting miles into airless skies. Worlds with mountains taller than anything on Earth. Worlds with seas made not of water, but of liquid methane. Worlds that should be frozen and dead, and are not. The moons of our solar system are among the most extreme environments ever discovered, and most of them are unknown to most people alive. We begin with the one that is on fire. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. In March of 1979, 3 days after Voyager 1 had already passed its closest point to Jupiter, a navigation engineer named Linda Morabito was processing images of Io when she noticed something wrong with one of them. She was not looking for volcanoes. Nobody was. The task in front of her was routine navigation work, checking star positions in the background of the image to confirm the spacecraft's location. But there was something in the photograph that did not belong. On the edge of Io's disk, rising above the surface, was a faint umbrella-shaped structure. It looked like a cloud. Io does not have clouds. Morabito stared at it. She ran through alternative explanations. Another moon, an image artifact, a smear in the processing. None of those held up. What she was looking at, extending nearly 200 miles above the surface of this small moon, was the plume of an active volcanic eruption, the first ever detected on any world other than Earth. Io had been assumed to be a cold, dead, heavily cratered rock. The image on her screen said otherwise. What made the discovery stranger still was that someone had predicted it. 8 days before Voyager 1's closest approach, a paper was published by a team of researchers, including Stanton Peele, suggesting that Io might be volcanically active. The physics were compelling. Jupiter is the largest planet in the solar system. Its gravity is enormous. Io orbits close, and as it does, it is being pulled on not just by Jupiter, but by Europa and Ganymede, 2 other large moons farther out. Their gravitational tugs push and pull on Io's orbit, keeping it slightly elliptical rather than perfectly circular. Because the orbit is not a perfect circle, Io's distance from Jupiter changes as it goes around. Jupiter's gravity is stronger when Io is closer, weaker when it is farther. The result is that the moon gets squeezed and stretched continuously as it orbits. Not gently, relentlessly. Think about what happens when you bend a metal paperclip back and forth. Do it 20 times fast, and the metal at the bend gets warm. Do it long enough, and it snaps. Io has been doing the equivalent of this for billions of years, and the heat produced by all that internal flexing has nowhere to go except up. It erupts. The prediction and the discovery arrived within 8 days of each other. Peale and his co-authors heard about Morabito's image just as their paper was being published. The timing was extraordinary. The surface Voyager revealed, and that subsequent spacecraft have mapped in increasing detail, is unlike anything else in the solar system. There are more than 400 active volcanoes on Io. Not dormant volcanoes, not ancient calderas, active ones, erupting now, reshaping the surface continuously. The ground in some regions is liquid lava. In others, it is plains of sulfur that shift color depending on temperature, running from white to pale yellow, to deep orange, to red to black, as you move from cooler deposits to hotter ones. If you could stand on Io and look at the horizon in any direction, you would see something erupting. Mountains rise above those plains, some taller than Everest, some significantly taller. The tallest known peak on Io reaches roughly 11 miles above the surrounding terrain. On Earth, mountains that large are built by tectonic plates grinding together. Io has no tectonic plates. Its mountains form through a different mechanism entirely. The surface of Io is being constantly buried under fresh volcanic material. Lava flows, sulfur deposits, ash, ejecta from plumes, all of it piles up. As new material accumulates on top, the older material beneath it gets pushed down. That constant downward pressure on buried rock eventually forces some of it back up through fractures, and where it pushes up, mountains form. Not from plates colliding, but from the sheer weight of continuous deposition pressing down for millions of years. The mountains are a byproduct of the volcano rate. The more violently a world resurfaces itself, the more it builds its own highlands by compression. There are no craters on Io, not because it has never been struck by meteorites, but because any crater that forms is buried or flooded or eroded away by volcanic activity before it has time to be preserved. The entire surface has been replaced, probably many times over, within the last few million years. That is an almost incomprehensibly fast geological pace. The Moon has craters that have sat unchanged for 4 billion years. Io cannot hold a crater for even a fraction of that time. Loki Patera sits near the equator. It is a lava lake, and it is enormous. The surface area of Loki Patera is larger than Lake Ontario. This is not a metaphor for scale. This is a comparison of actual area. The lake is covered by a crust of cooled and solidifying lava, but periodically that crust overturns. Fresh, hot magma from beneath breaks through. The cooler crust sinks, and a wave of bright new lava spreads across the surface of the lake. This overturn happens roughly every 1 to 2 years, and it is regular enough that astronomers on Earth can predict when it will occur and watch it happen through ground-based telescopes. A lava lake on a moon of Jupiter, 400 million miles away, running on a schedule precise enough to observe from here. Loki Patera has been doing this, as far as researchers can tell, for as long as anyone has been watching. The plumes are what make Io's volcanism visible across enormous distances. Some of Io's volcanic eruptions send material not just into the air, but out into space. In an environment with no real atmosphere to slow them down, volcanic plumes on Io can reach heights of 300 miles. They expand into the vacuum above the surface, and then the material falls back down, spreading outward in a ring. From orbit, these ring-shaped deposits are visible on the surface, sometimes hundreds of miles across, centered on the vent that produced them. They are not rings of rock. They are rings of sulfur dioxide frost, bright white against the orange and yellow plains. Some of the larger plume fields have been visibly reshaped between one spacecraft's visit and the next. Not all of what Io erupts comes back down. A fraction of the material escapes Io's weak gravity entirely and enters orbit around Jupiter. Over time, this volcanic output has built up a donut-shaped cloud of ionized gas called the Io plasma torus. It wraps around Jupiter along the path of Io's orbit, glowing faintly in ultraviolet light, a permanent feature of the Jovian system. Io is physically losing mass to Jupiter. Every eruption contributes a small fraction of material to this torus. The Moon is being consumed, slowly, by the gravity that makes it so violent in the first place. Jupiter's radiation belts are intense at Io's distance. The charged particles trapped in Jupiter's magnetic field bombard Io's surface constantly, breaking down sulfur compounds, sputtering material off into space, adding to the plasma torus. Io is embedded in one of the most hostile radiation environments in the solar system. Any spacecraft that attempted to orbit Io for an extended period would have its electronics degraded within weeks. Galileo, the spacecraft that spent 8 years studying the Jupiter system, was deliberately sent into Jupiter's atmosphere at the end of its mission to avoid contaminating the moons. During its close flybys of Io, the radiation began affecting its instruments in measurable ways. Even brief visits cost something. What the Galileo flybys confirmed was what Voyager had only glimpsed. The volcanic activity on Io is not localized to a few regions. It is global. Heat is escaping from the interior at a rate far higher than any other rocky body in the solar system. Earth has volcanoes because its interior is still warm from formation and from the decay of radioactive elements. Io's heat comes primarily from tidal flexing, an external mechanical source that will continue as long as Europa and Ganymede hold their current orbital positions, which means as long as Jupiter exists. The engine is not running down. There is a version of a moon you probably carry in your head. Pale, cold, cratered, silent. That image comes from our own moon, which is geologically quiet and has been for billions of years. Io dismantles that image entirely. It is a moon the size of Earth's moon, in orbit around a gas giant, and it is the most geologically violent body in the entire solar system. Not the most active planet, not the most active rocky world. The most active body we have found anywhere, full stop. Its surface is being continuously rebuilt. Its mountains are growing and collapsing. Its lava lakes are turning over on schedules you could put in a calendar. And it is actively contributing material to the space around its planet in quantities large enough to form a structure visible from Earth. Somewhere on Io right now, a volcano is erupting, a lava lake is overturning, and sulfur is raining back down onto a surface that will look nothing like this in another 1,000,000 years. About 400,000 miles from Jupiter, smaller than our own moon, and wrapped in a shell of water ice, sits what many planetary scientists consider the most important object in the solar system outside of Earth itself. Europa looks nothing like Io. Where Io is orange and yellow and constantly tearing itself apart, Europa is pale and quiet and almost featureless from a distance. Smooth, almost glassy, with a surface that reflects sunlight so cleanly it shines like polished bone against the black of space. But that smoothness is not a sign of calm. It is a sign of something working underneath. A surface this smooth means craters are not surviving. Impact scars that would persist for billions of years on a dead world are being erased, slowly and continuously, as the crust above whatever is below shifts and refreezes and shifts again. Europa's surface is young. Geologically speaking, it is practically new. And in planetary science, a young surface almost always means something is still active beneath it. The cracks tell you more. Stretch across Europa's face in every direction, reddish-brown and sharp, are long fractures called lineae. Some of them run for thousands of miles. They cross each other, bend, fade, then resume. The color comes from something mixed into the ice along those lines, something that is not pure water. The leading explanation is that these fractures are places where the ice has split open, ocean water has welled up into the gap, and radiation from Jupiter has cooked whatever salts and minerals were dissolved in that water into reddish organic compounds. If that is right, then the staining you can see across Europa's surface from orbit is essentially sea salt, processed and darkened, marking every place where the ocean below has touched the outside world. The same force that is destroying Io is at work here, but quieter. Jupiter's gravity is immense, and Europa sits close enough to feel its pull unevenly across its own body. Europa and Ganymede and Io are locked in a gravitational rhythm with each other, each tugging slightly as they orbit, and the result is that Europa's shape flexes on every orbit. Not dramatically, not enough to crack the crust wide open the way Io is cracked. Just enough. Just enough heat to keep water liquid far below the surface in an environment that, by any reasonable estimate, should be frozen solid to the core. This is tidal heating doing something different than it does at Io. At Io, it is turning the interior into a furnace. At Europa, it is keeping a light on. Barely warm enough. Precisely enough. The ocean beneath the ice has not frozen because Jupiter will not let it freeze. The evidence for the ocean is not theory, it is measurement. When the Galileo spacecraft flew past Europa in the late 1990s, it carried a magnetometer. Jupiter produces one of the most powerful magnetic fields in the solar system, and that field washes over everything in orbit around it. When Galileo measured the way Europa responded to Jupiter's magnetic field, the readings were not what you would expect from a ball of rock and ice. They were what you expect from a conductor. Something inside Europa was responding to the changing magnetic field, the way a salty liquid responds. The induced magnetic field that Galileo detected matches almost exactly what you would predict if Europa had a global layer of electrically conductive fluid just below its surface. Salt water is an excellent conductor. Ice is not. The ocean is not a hypothesis built on wishful thinking. It is the explanation that fits the magnetic data. What nobody agrees on is how thick the ice shell above that ocean actually is. The debate has been running for decades. Some researchers look at the surface features and argue for a shell no more than 10 miles deep, possibly thinner in places. Others look at thermal models and the way certain surface structures appear to form and argue for something closer to 60 miles. The difference is not academic, A 10-mile ice shell is a very different world from a 60-mile one. A thinner shell is more likely to be fractured all the way through in places, more likely to allow material to cycle between the ocean and the surface, more likely to produce the kind of exchange that could carry chemical energy from the ocean up toward the ice and back. A 60-mile shell is closer to a sealed vault. The ocean inside is still there, still liquid, but it is far more isolated. Whether life needs that exchange or not is a separate question. But the thickness of the ice matters enormously to how we think about what might be happening inside. The ocean itself, by best current estimates, holds roughly twice the volume of all Earth's oceans combined. Twice the water, compressed beneath miles of ice, sitting above a rocky ocean floor that has never seen sunlight. It is dark down there in a way that is hard to describe. Cold above, where the ice meets the water, but not necessarily cold at the bottom. If Jupiter's tidal forces are flexing the ocean floor the same way they flex the crust above, there is heat being generated at depth. Heat at the floor of an ocean sitting above rock is something we understand from Earth. On Earth, hydrothermal vents on the deep seafloor release superheated water laced with minerals into the surrounding ocean. The organisms that live around those vents have no connection to sunlight whatsoever. They run entirely on chemical energy. Bacteria, tube worms, crabs, shrimp, fish. Entire ecosystems built in complete darkness around the heat and chemistry of the rock below. If Europa's ocean floor is being warmed from below, the conditions for something like that may exist in a place that has never seen a photon from the sun. The chemistry matters as much as the heat. On Earth, hydrothermal vents work because water and rock react. Hot water moving through rock dissolves minerals, strips hydrogen, carries energy that certain microorganisms can metabolize. The reaction that drives that chemistry is not exotic. It requires liquid water, rock, and heat. Europa appears to have all three. The ocean is in contact with a rocky floor. The tidal heating provides warmth at depth, and the water has been there long enough to have dissolved whatever the rock has to offer. The reddish material in the lineae suggests the ocean is not pure. It carries things. Whatever those things are, they have been cycling in that water for a very long time. The Europa Clipper mission launched in 2024 and is currently crossing the solar system toward the Jupiter system. It is not a lander. It will not drill through the ice. What it will do, through dozens of close flybys, is map the surface in extraordinary detail, measure the magnetic field with far more precision than Galileo could manage, search for active plumes like the ones seen at Enceladus, and attempt to determine how thick the ice shell actually is. If it finds plumes, the implications are significant. Plumes from Enceladus have already told us what that moon's ocean contains, sampled by a spacecraft flying through them without needing to land at all. If Europa is also venting its ocean into space in any form, even intermittently, Clipper will be positioned to taste it. The mission arrives in the early 2030s. The data it returns will rewrite what we know about this moon regardless of what it finds. The age of the ocean is its own kind of fact. Europa has probably had liquid water beneath its surface for billions of years. Not hundreds of millions. Billions. The tidal mechanism that heats it now was in place shortly after Jupiter's moon system formed and stabilized into its current orbital resonance. That ocean has been sitting in contact with rock, cycling whatever chemistry the water and the floor produce between them, for longer than the Cambrian explosion is from now. longer than complex multicellular life has existed on Earth. Whatever processes are running in that water have had enormous time to run. Whether that time has produced anything is the question we cannot answer from here. Whatever is down there has had longer to develop than complex life has been on Earth, and we have never sent anything to look. If Ganymede were orbiting the Sun instead of Jupiter, there would be no debate about what to call it. It would be a planet, larger than Mercury, larger than Pluto, larger than every dwarf planet we have catalogued in the outer solar system. The only reason it carries the word moon in its name is that Jupiter got to it first. At 3,270 miles across, Ganymede is the largest moon in the entire solar system, and it is not close. Mercury is a full planet with its own entry in textbooks and its own place in the classical order of the solar system. Ganymede is wider. This matters not just as a piece of trivia, but as a framing device, because the assumptions that come with the word moon, small, cold, inert, geologically dead, do not apply here. Ganymede has a rocky iron core. Surrounding that core is a deep mantle of water ice, potentially layered with pockets of liquid water sandwiched between different phases of high-pressure ice. Above that is an outer crust of mixed rock and ice. The interior of Ganymede is more complex than the interior of many objects we call planets. It is not a simple frozen ball. It is a structured, differentiated world with distinct layers, each behaving differently under the pressure and temperature conditions specific to its depth. The ice mantle is worth pausing on. Water behaves strangely under extreme pressure. It does not simply remain solid or liquid. It transitions through multiple crystalline phases, each with different densities and properties. Researchers believe that inside Ganymede, layers of liquid water may be trapped between layers of different ice phases, stacked one on top of another like a geological layer cake. The total volume of water in this system could be enormous. Estimates suggest Ganymede holds more liquid water than exists on the entire surface of Earth. This is not confirmed, but the internal structure models are consistent enough that it is taken seriously by planetary scientists. Then there is the magnetic field. This is where Ganymede stops being surprising and starts being genuinely strange. Ganymede is the only moon in the solar system known to generate its own global magnetic field, not a residual magnetism frozen into old rock. A living, active magnetic field produced by something churning inside the moon right now. To generate a magnetic field this way, you need a core that is at least partially molten, electrically conductive, and actively moving. Ganymede apparently has all three. The dynamo running inside this moon is producing a magnetosphere, a region of space shaped by Ganymede's own magnetic influence, sitting inside Jupiter's far larger magnetosphere. The two fields interact. Where Ganymede's field meets Jupiter's, the charged particles trapped in Jupiter's magnetosphere get funneled down along Ganymede's magnetic field lines and slam into the moon's polar regions. The result is auroras, visible auroras. The Hubble Space Telescope has observed them directly, glowing bands of ultraviolet light near Ganymede's poles, a moon with its own auroras. That is not a description that fits easily into the category of small airless rock. The surface of Ganymede is divided into two distinct types of terrain, and the contrast between them is sharp enough to be obvious in photographs taken from millions of miles away. The darker regions are ancient. They are heavily cratered, scarred by billions of years of impacts, and largely unchanged since the early solar system. The lighter regions are something else entirely. They are grooved. Long parallel ridges and troughs cut across them in sweeping bands. The craters in these zones are fewer, meaning the surface is younger, meaning something reshaped this terrain after the heavy bombardment period ended. Whatever happened was large enough in scale to affect roughly a third of Ganymede's surface. It involved stretching, faulting, possibly the upwelling of warm material from below. And the honest answer is that nobody has a complete explanation for why it happened, when exactly it happened, or what drove it. The grooved terrain of Ganymede is one of the more significant unsolved problems in outer solar system geology. In June of 2021, NASA's Juno spacecraft swung close to Ganymede, the closest any spacecraft had come in more than 2 decades. Juno was designed primarily to study Jupiter, but its instruments were pointed at Ganymede for the flyby. The data it collected on the magnetosphere was detailed in ways earlier missions had not been able to achieve. Juno found that Ganymede's magnetic field is more structured than simple models suggested, with complexity in how it connects to and interacts with Jupiter's field. The plasma environment around the Moon, the mix of charged particles trapped in the combined magnetic system, turned out to be richer and more dynamic than expected. Juno also captured surface imagery sharper than anything available since the Galileo mission's close passes in the late 1990s. The images showed both terrain types in high resolution and added texture to what researchers already knew, without resolving the deeper questions about what caused the grooved regions. A spacecraft is now on its way to go much further. JUICE, the Jupiter Icy Moons Explorer, built by the European Space Agency, launched in 2023. It is heading to the Jupiter system with Ganymede as its primary long-term target. The plan is not a flyby. JUICE will eventually enter orbit around Ganymede, becoming the first spacecraft ever to orbit a moon other than our own. From orbit, it will study the magnetic field in fine detail, map the surface comprehensively, probe the interior using radar and gravity measurements, and work toward a clearer picture of whether that layered internal ocean is real and how extensive it is. The largest moon in the solar system generates its own magnetic field, possibly has a layered internal ocean, and we still do not know what happened to reshape half its surface billions of years ago. Callisto looks like a world that gave up, where Io is erupting constantly and Europa's surface is being cracked and reformed by an active ocean below. Callisto just sits there, frozen, battered, unchanged. Every impact it has absorbed over 4 billion years is still exactly where it landed. There are no volcanoes resurfacing the crust, no tidal forces flexing the interior, no geological process of any kind smoothing things over. What you see on Callisto is what the early solar system did to it, preserved in full, like a photograph that was never disturbed. Scientists have a name for surfaces like this. They call it a saturated crust, meaning there are so many craters that new ones are simply forming on top of old ones. You cannot pack more impacts into it. The surface is full. This makes Callisto genuinely useful in a way that Io and Europa are not. Because nothing has been erased, the Moon carries a direct record of the period astronomers call the Late Heavy Bombardment, a phase roughly 4 billion years ago when the inner solar system was being hammered by an enormous flux of asteroids and comets. That record has been wiped clean on most worlds. Earth's craters are mostly gone, eroded by weather and plate tectonics. Io's surface is being replaced so fast that nothing older than 1,000,000 years survives. Europa's ice has been recycled. Callisto kept everything. If you want to understand what the early solar system was throwing around, Callisto is one of the only places left where you can still read that history directly off the ground. The most dramatic feature on that ancient surface is a structure called Valhalla. It sits near the center of Callisto's Jupiter-facing hemisphere, and from above it looks like a target. There is a bright central plane roughly 360 miles across, then ring after ring after ring spreading outward from it, each one a concentric arc of ridges and scarps, reaching nearly 2,000 miles from the center before they fade out. The collision that made Valhalla was so powerful that it sent waves rippling outward through the crust in every direction. Those waves simply froze in place before they could dissipate. What remains is a permanent record of that single moment of impact, locked into the surface for billions of years. Nothing on Callisto has been active enough to erase it. Valhalla is still there, more or less exactly as it was left. Across the rest of the surface, something subtler is happening. In the lower lying areas between craters, the bright ice that makes up much of Callisto's crust has been slowly disappearing. Ice exposed to space at Callisto's distance from the Sun will sublimate over long enough timescales, converting directly from solid to vapor without melting. As it does, whatever non-ice material was mixed in with it gets left behind, accumulating on the surface in a thin, dark layer. This material is probably a mix of rocky minerals and organic compounds. It tends to collect in the low spots while the higher ground stays brighter. The result is a surface that gets progressively darker and more muted with age. The bright crater rims standing out sharply against terrain that has had billions of years to accumulate this dark residue. None of this suggests anything is happening inside Callisto. The surface has no features that would point to internal heat, no young terrain, no sign of any tectonic or volcanic process. By every visual measure, this is a dead world, which is why the readings from the Galileo spacecraft's magnetometer were unexpected. When Galileo made several close passes of Callisto in the late 1990s, its instruments detected a response in Callisto's magnetic environment that was difficult to explain without invoking a conducting layer somewhere beneath the surface. The pattern was similar to what Galileo found at Europa, where a salty subsurface ocean was generating a detectable electromagnetic signature. Callisto showed something weaker and less clear, but it was there. The most straightforward explanation is a subsurface ocean of liquid salt water, buried deeper than Europa's and far more uncertain, but possibly present. For a world that looks completely inert on the outside, this was a genuinely strange result. If there is an ocean inside Callisto, it would have to be maintained by something. The most likely candidate is a small amount of residual radioactive decay in the rocky material throughout the interior. There is no evidence of tidal heating the way Europa or Io experience it. Callisto sits farther from Jupiter and is not caught in the orbital resonance that drives the inner moons. Whatever heat Callisto generates is coming from within the rock itself, slowly, without drama, the fading warmth of ancient radioactive elements. Just enough, possibly, to keep a thin layer of briny water liquid somewhere in the deep interior. That same distance from Jupiter that makes Callisto geologically quiet also makes it, in a practical sense, one of the more hospitable places in the Jupiter system for anything we might want to send there. Closer in, near Io and Europa, Jupiter's radiation belts are intense enough to threaten both electronics and human biology. Callisto sits outside the worst of it. Several studies have looked at Callisto as a possible base for crewed operations in the Jupiter system, a staging point from which robotic vehicles could be sent deeper in to explore the more scientifically compelling but far more dangerous moons. A dead world used as a doorstep to the ones that are not. The most cratered moon in the solar system, the one that shows no signs of life on its surface at all, may be hiding an ocean underneath. The atmosphere on Titan is thicker than Earth's, not slightly thicker. At the surface, the pressure is about 1.5 times what you feel standing at sea level on this planet. If you were somehow standing on Titan without a spacesuit, the pressure alone would not kill you immediately. The cold would. The surface temperature sits around -290 degrees Fahrenheit. But the atmosphere itself, that dense orange shroud wrapping the entire moon, is breathable in one specific sense. It is mostly nitrogen, the same gas that makes up 78% of Earth's air. You would suffocate, but you would not be crushed. That is a strange thing to say about a moon of Saturn. Titan is Saturn's largest moon and the second largest moon in the entire solar system. It is bigger than Mercury. It is the only moon anywhere in the solar system with a thick, substantial atmosphere. And that atmosphere does something remarkable. It drives weather. Real weather. Not the kind of weather scientists describe cautiously with words like possible or inferred. Actual clouds, actual rain, actual rivers and lakes and seas sitting on the surface, mapped and measured by spacecraft. The catch is that none of it involves water. The liquid on Titan is methane. Liquid methane and its chemical cousin ethane, filling lake basins and carving river channels and raining out of orange clouds onto a frozen landscape that, from the right angle, looks almost familiar. In January of 2005, a probe called Huygens descended through Titan's atmosphere and became the most distant object humanity has ever landed on. It took 2.5 hours to fall through the haze. It transmitted data the entire way down. When the images came back, planetary scientists went quiet for a moment. The landscape looked wrong in a specific way. It looked like somewhere you might recognize. Rounded pebbles covered the surface near the landing site, worn smooth by flowing liquid exactly the way river rocks are worn smooth on Earth. Except these pebbles were made of water ice, hard as granite at Titan's temperatures. Channels were carved into the terrain above. Flat plains stretched out toward the horizon, pale and etched with patterns that looked like dried riverbeds. The Huygens probe had landed in the middle of something that resembled a floodplain. No water had put it there. Methane had. The methane cycle on Titan mirrors the water cycle on Earth almost step for step. Liquid methane on the surface evaporates into the atmosphere. It rises, cools, and condenses into clouds. Those clouds produce rain that falls back to the surface, collects in low-lying basins, carves channels through ice and rock, and eventually drains toward the poles where the largest bodies of liquid on the moon accumulate. Then it evaporates again. The cycle repeats. It has been repeating for an enormously long time. Earth's water cycle built canyons and deltas and oceans over billions of years. Titan's methane cycle has been doing the same thing, on a moon where the average surface temperature would instantly freeze any water solid. The seas near Titan's North Pole are not small. Ligeia Mare covers an area roughly the size of Lake Superior and Lake Michigan combined. Kraken Mare is larger than the Caspian Sea, the largest landlocked body of water on Earth, and it stretches across hundreds of thousands of square miles of Titan's northern hemisphere. These are not puddles. These are oceans of liquid methane and ethane sitting quietly beneath an orange sky, calm enough that radar measurements from the Cassini spacecraft detected almost no surface waves at all. Titan's seas are still in a way that Earth's oceans never are. The composition of these liquids is not pure methane. Ethane comprises a significant fraction, with trace amounts of other organic compounds mixed throughout. The depths of these seas remain unmeasured, though some estimates suggest they may rival Earth's oceans in places, creating enormous reservoirs of liquid hydrocarbons. The density of methane and ethane is lower than water, a fact with strange implications for buoyancy and for any future underwater exploration of these worlds. Cassini spent 13 years in the Saturn system and mapped Titan repeatedly through its opaque haze using radar. The picture it built up is of a world with distinct geography: dune fields near the equator, river networks at mid-latitudes, seas and lakes clustered toward the poles. The North Pole has the most liquid. The South Pole has some. The equatorial region is mostly dry, dominated by enormous fields of dark dunes made not of sand, but of organic particles that have rained out of the atmosphere over millions of years. Each region looks and behaves differently. Titan has climate zones the way Earth does. Cassini's observations revealed not just static bodies of liquid, but evidence of seasonal variation in Titan's methane cycle, with surface features suggesting that methane flows across the landscape as seasons change. The southern seas, though smaller than those at the North Pole, still represent enormous bodies of liquid comparable to the largest lakes on Earth. Here is where the chemistry becomes strange. Methane in an atmosphere does not last. Ultraviolet radiation from the sun breaks methane molecules apart relatively quickly on geological timescales. If nothing were replacing the methane in Titan's atmosphere, it would be gone. The atmosphere would collapse, the seas would drain, the weather would stop. But none of that has happened. Titan's atmosphere is full of methane right now, which means something is actively replenishing it. The leading hypothesis is that Titan's interior is the source. Methane venting from the interior, possibly through cryovolcanism, meaning eruptions not of molten rock, but of volatile compounds from a warmer interior into the frigid surface environment. The mechanism is not confirmed. No one has caught Titan actively venting. But the alternative is that this atmospheric methane has somehow persisted for billions of years without replenishment, which the chemistry does not support. The source of Titan's replenishing methane could be anything from internal venting to chemical reactions occurring in the subsurface ocean. Cryovolcanism on Titan, if it is indeed occurring, represents a fundamentally different mechanism of planetary replenishment than the volcanism familiar from volcanic worlds like Earth or Venus. Above the surface, above the clouds, the atmosphere does something else entirely. Nitrogen and methane in the upper atmosphere are struck by ultraviolet light and charged particles streaming out from the sun. The energy breaks these molecules apart and drives them to recombine into more complex structures. The products are called tholins, a broad class of reddish-brown organic molecules that form a thick photochemical smog wrapping the entire moon. This smog is what gives Titan its color. From space, it looks like a fuzzy orange ball, completely featureless, no surface detail visible in ordinary light. The haze is global and permanent. It filters out most of the sunlight before it reaches the surface, leaving the ground perpetually dim, lit roughly the way Earth looks just after sunset. Tholins are not just atmospheric pollution, they are chemically significant. Some of the organic molecules forming in Titan's upper atmosphere are the same classes of compounds found in the prebiotic chemistry of early Earth, the building blocks that, under the right conditions, can lead to amino acids and more complex biological molecules. On Titan, they rain out of the sky and accumulate in dune fields that stretch for thousands of miles. The equatorial dunes are made substantially of this material, dark and organic, piling up in ridges that Cassini's radar tracked across enormous distances. Titan's surface is being continuously coated in the products of atmospheric chemistry that resembles something from a laboratory study of life's origins. The organic smog raining onto the surface has accumulated over millions of years. Some estimates suggest the dune fields contain billions of tons of these organic materials. Wind speeds on Titan are generally low compared to Earth, creating a relatively placid environment for these chemical processes to unfold. The chemical reactions occurring between organic molecules and methane on Titan's surface create environments unlike anything found elsewhere in the solar system. Whether any of this chemistry goes further is unknown. Titan is far too cold for liquid water, which most biochemistry as we understand it requires. But some researchers have proposed that entirely different forms of chemistry could operate in liquid methane, using it the way life on Earth uses water. This is speculative. Nobody has found evidence for it. But Titan is the only place in the solar system, other than Earth, where stable liquids pool on a surface, where rain falls and rivers run, and where complex organic chemistry is actively happening on a planetary scale. That combination makes it worth looking at very carefully. The Dragonfly mission is going to do exactly that. Dragonfly is a rotorcraft lander, essentially a large drone, nuclear-powered, designed to fly through Titan's thick atmosphere from site to site, rather than rolling slowly across the surface the way a rover does. It is scheduled to arrive in the 2030s. The dense atmosphere that makes Titan so strange also makes flight relatively easy compared to somewhere like Mars, where the air is so thin that rotorcraft struggle. On Titan, you can fly with much less effort. Dragonfly will land near the equatorial dune fields first, sample the organic material sitting there, and then fly to other sites, potentially including the rim of a crater where water ice and organic molecules may have mixed in liquid water during the impact's heat, creating conditions that briefly resembled early Earth's chemistry. Each landing site is a different laboratory. Each one will give a different chemical snapshot of what Titan's surface is made of and what reactions are happening there. Somewhere below those orange clouds, methane rain is falling into seas the size of terrestrial oceans, and in the 2030s, a spacecraft shaped like a dragonfly is going to land there and start looking around. Enceladus is 300 miles across. That is smaller than the state of Arizona. It is smaller than most mid-sized countries. By the standards of the outer solar system, it is barely a footnote. Objects this small run out of internal heat quickly. The physics are straightforward. Small bodies have more surface area relative to their volume. They radiate heat into space faster, and within 1 billion years or so, they cool into inert frozen rock. Enceladus has had 4.5 billion years to do exactly that. There should be nothing left. No heat, no geology, no activity of any kind. Just a cold, cratered, silent ball of ice drifting around Saturn. And yet, in 2005, the Cassini spacecraft swung around Saturn's southern hemisphere and aimed its instruments at Enceladus. What it found stopped the mission team cold. Erupting from the south pole of this tiny, supposedly dead moon were enormous geysers. Not small leaks, not trace emissions. Vast curtains of water vapor and ice particles blasting hundreds of miles into space, catching the light of the distant sun in brilliant plumes that towered over the surface. Cassini had not been sent to Enceladus expecting anything like this. Nobody had. The discovery rewrote the mission's priorities almost overnight. The geysers were not just spectacular, they were consequential. Saturn's E-ring, the broad, diffuse ring that sits beyond the main ring system, had always been a slight puzzle. It is younger than the others, more tenuous, made of particles too small and too loosely bound to have survived billions of years in space. It needed a source. Cassini found it. Enceladus sits almost exactly at the center of the E-ring, and its geysers are continuously injecting fresh material into it. This tiny moon is actively building one of Saturn's rings. Every second, hundreds of kilograms of ice and vapor are being launched off the surface and into the surrounding space. Some of it falls back. A great deal of it does not. What this meant was profound. A small moon was not merely leaking, it was actively sculpting its planetary environment. The E-ring would not exist without Enceladus. The ring's composition, its distribution, its gradual dissipation over time, all of it traces back to this single source. The implications rippled through planetary science. If a tiny moon could be geologically active enough to feed an entire ring system, what else might be happening in the outer solar system that conventional models had dismissed as impossible? The source of the eruptions narrows to 4 specific fractures near the South Pole, running roughly parallel to each other. They have a name now, the Tiger Stripes. Each fracture is about 85 miles long. They are separated by roughly 25 miles of terrain, evenly spaced, running almost perfectly parallel. The Tiger Stripes are warmer than the surrounding surface by a measurable margin. In the frigid environment around Saturn, where temperatures drop to around -300 degrees Fahrenheit, even a modest temperature difference stands out clearly to an infrared instrument. The stripes are warm, and from those warm fractures, the plumes rise. The precision of their geometry is itself notable. 4 parallel lines, evenly spaced, running for dozens of miles without deviation. Such perfect symmetry suggests deep structural control. These fractures are not random cracks in the surface. They are expressions of something fundamental about Enceladus's interior. The cracks appear to be ancient features, possibly formed early in the moon's history, that have been reactivated by ongoing interior processes. They represent weak points in the ice shell, where internal pressure finds the path of least resistance to escape. The heat is the part that does not make sense. Enceladus is too small and too far from Saturn to generate the amount of energy it is putting out through tidal heating alone. Tidal heating works. It is the same mechanism squeezing Io into a volcanic hellscape, the same gentle version warming Europa's ocean. But the amount of heat tidal forcing should produce in a body this small, at Enceladus's distance from Saturn, falls short of what is actually measured at the South Pole by a significant margin. The numbers do not close. Something inside Enceladus is generating more energy than the standard calculations allow. The exact mechanism is not settled. Some researchers believe the tidal heating is concentrated specifically in the South Polar region in ways that are more efficient than a uniform model would suggest. Others think the Moon's interior has properties that amplify the effect. Whatever the answer, Enceladus is hotter than it has any right to be, and the heat is escaping through those 4 parallel cracks. What the plumes are made of tells the more important story. Cassini did not just photograph the geysers, it flew through them. Directly through the plume material, with instruments open and collecting data. Water vapor was expected. Ice particles were expected. What Cassini also found was sodium chloride, table salt, carbon dioxide, molecular hydrogen, silica particles of a very specific size range, and complex organic molecules, the kind assembled from carbon, hydrogen, nitrogen, and oxygen in combinations that suggest active chemistry. Each of these components is a message. Salt in the plume means the water it came from has been sitting in contact with a rocky seafloor. Ocean water picks up salts by dissolving minerals from rock over time. Earth's oceans are salty for exactly this reason. The presence of sodium chloride in Enceladus's plumes means there is an ocean, and that ocean has a rocky bottom it has been interacting with for a long time. That alone would be remarkable. But the silica particles go further. Silica particles of a specific size, nanometer-scale grains, form only under a narrow set of conditions. Hot water, above roughly 90 degrees Celsius, flowing through silicate rock, precipitates silica grains in that size range. Below that temperature, the chemistry does not produce them. Above a certain temperature, the grains grow larger. The particles Cassini found in the plume of Enceladus are the right size. That means hydrothermal vents. Somewhere on the floor of Enceladus's ocean, hot water is flowing through rock the same way it does at Earth's mid-ocean ridges. Molecular hydrogen fits the same picture. Hot water reacting with certain minerals in a process called serpentinization releases molecular hydrogen as a byproduct. Cassini detected it. The ocean floor of Enceladus appears to be actively reacting with hot water. On Earth, deep ocean hydrothermal vents support entire ecosystems with no sunlight whatsoever. Bacteria, tube worms, shrimp, crabs, communities of life powered by chemical energy rather than solar energy. The vent fluids carry hydrogen and sulfur compounds that microbes can metabolize. Enceladus appears to have the same basic setup: warm, salty water, a rocky floor, hydrothermal activity, chemical energy in the form of molecular hydrogen. Whatever life needs from a hydrothermal environment, Enceladus seems to have it. These Earth-based vent ecosystems thrive in complete darkness, thousands of meters below the ocean surface, where sunlight never penetrates. They prove that life does not require sunlight as an energy source. The bacteria and other microorganisms that cluster around hydrothermal chimneys extract chemical energy directly from the minerals dissolved in the vent water. This chemosynthetic metabolism is fundamentally different from photosynthesis, but it is no less effective at sustaining complex communities. The ocean of Enceladus, if it harbors life, would operate on the same principle: chemistry rather than sunlight as the foundation of its food web. The organic molecules complicate the picture further. Some of what Cassini detected in the plume was relatively simple: methane, carbon dioxide. But some of the molecules were heavier and more complex, with structures that do not form easily through random processes. Complex organics in a warm, salty, chemically active ocean in contact with a hydrothermal floor. The researchers who analyzed that data were careful about their language. They did not claim life, but they noted that the chemistry being detected inside that plume was the kind of chemistry that, on Earth, tends to have biology behind it. Consider what Cassini actually did. It flew a spacecraft through the erupting output of an alien ocean. No drilling, no landing, no years of surface operations in a brutal environment. The ocean of Enceladus is sending itself into space, and all Cassini had to do was be in the right place. The mission team flew through the plume multiple times, each pass collecting more data, refining the picture. It is one of the least complicated pathways to ocean chemistry sampling that anyone has ever proposed for another world. And it happened not by design, but because Enceladus itself made it possible. The ocean this plume is drawing from sits beneath the south polar ice shell, possibly extending globally beneath the entire surface. The ice shell itself is thinner near the South Pole, which is part of why the venting happens there. Beneath that ice, liquid water. Estimates suggest the ocean contains a substantial volume, not enormous by Earth standards, but real, persistent, chemically active. It has probably been liquid for hundreds of millions of years, possibly longer. The tidal heating that maintains it has been running since Enceladus settled into its current orbital configuration. The implications of such stability are significant. An ocean that has remained liquid for such an extended period provides the kind of persistent environment where complex chemistry might develop, and potentially where life, if it exists, could evolve and adapt over deep time. There is a small moon. It has been orbiting Saturn since before complex life appeared on Earth. Inside it, an ocean sits in contact with a rocky floor. Hot water moves through that rock. Salt dissolves in. Hydrogen releases. Complex chemistry proceeds. And then the ocean erupts through cracks in the ice and sprays itself into space. A moon smaller than most US states is erupting its ocean into space, and we already flew through it. Giovanni Cassini discovered Iapetus in 1671 and was immediately confused by it. He was working at the Paris Observatory, scanning Saturn through one of the best telescopes available at the time, and he found a small point of light orbiting the planet at a considerable distance. He noted it. He tracked it. Then, as Iapetus moved around to the other side of Saturn, it disappeared, not faded, not dimmed slightly. Gone. He could not find it at all. For years, Cassini struggled to explain what he was seeing. He eventually concluded that one side of this moon must be bright, and the other side must be dark, and that the dark side was so dark the telescope could simply not pick it up. This was a reasonable conclusion. It was also correct. What he could not have known was just how extreme the difference actually was. Iapetus is tidally locked to Saturn, the same way our own moon is locked to Earth. It always shows the same face in the direction of its orbit. The hemisphere that faces forward as Iapetus moves is called the leading hemisphere, and it is covered in material so dark it reflects only about 3 or 4% of the light that hits it. Coal is slightly more reflective. The trailing hemisphere, by contrast, is bright white ice, reflecting close to 60% of incoming sunlight. These two surfaces sit right next to each other on the same moon, separated by gradual transition zones that still cover enormous distances. From a spacecraft looking down, the overall pattern looks almost exactly like a yin-yang symbol painted across a world roughly 900 miles wide. The first explanation that seemed intuitive was that Iapetus was sweeping up dark material as it moved through space, the way a car windshield collects insects. The leading hemisphere faces into the direction of travel, so anything drifting in its path would accumulate there. This turned out to be partly right. The dark material is real, it is external, and it does come from elsewhere in the Saturn system. Phoebe, a large captured moon orbiting Saturn in the opposite direction far out from the planet, sheds material constantly as micrometeorite impacts knock dust off its surface. That debris drifts inward. Iapetus, moving in the opposite orbital direction, collects it on its leading face. Other outer irregular moons contribute material in the same way. The coating that builds up over time is a reddish-brown organic crust. But that explanation alone does not get you to the extreme contrast Cassini observed in 1671. There are other moons that collect dark material on their leading hemispheres. None of them look like this. Something is amplifying the difference. The current model is called thermal segregation, and it works like a slow runaway process. Once dark material lands on the leading hemisphere, it absorbs more heat from the sun than the surrounding bright ice does. This warms the surface just slightly. At the temperatures present on Iapetus, that small temperature difference is enough to cause nearby ice to sublimate, converting directly from solid to vapor. That water vapor drifts and redeposits somewhere cooler, which means it moves toward the bright trailing hemisphere and refreezes there. Over time, the dark regions lose their ice, become darker still, absorb even more heat, drive off even more ice. The bright regions gain ice, become more reflective, stay cooler, hold on to their ice. Each cycle amplifies what was already there. Run this process for hundreds of millions of years, and the result is one of the starkest surface contrasts on any object in the solar system. What makes Iapetus genuinely strange is that neither the dark coating nor the thermal feedback alone produces this pattern. You need both. The organic material from Phoebe seeds the dark regions in the right place, and then thermal segregation takes over and pushes both hemispheres toward their extremes. Take away either factor and the contrast collapses. With both, you get a moon that a 17th century astronomer could watch vanish through his telescope. None of that explains the ridge. Running almost exactly along the equator of Iapetus is a mountain range, not a small one. The ridge extends for roughly 800 miles and rises in places to about 12 miles above the surrounding terrain. That is taller than anything on Earth. Olympus Mons on Mars, which is the largest known volcano in the solar system, reaches about 16 miles. The equatorial ridge on Iapetus is in that category of height, sitting on a moon less than 1,000 miles across. In some sections, it forms a single sharp spine. In others, it breaks up into a chain of isolated peaks. From orbit, it looks almost artificial, a seam running around the middle of the world like a mold line on a plastic ball. Nobody has a satisfying explanation for it. One hypothesis is that Iapetus once had a ring of its own, material orbiting close to the moon that eventually lost energy and collapsed inward, settling along the equator and piling up over time. The equatorial alignment would support this. The problem is that the physics of how that material would have accumulated into mountains, rather than simply coating the surface evenly, is not well understood. Another hypothesis involves internal tectonics early in the moon's history. some kind of equatorial stress or compression as the body cooled and contracted. This also struggles under detailed modeling. The equatorial ridge remains one of the more genuinely unresolved features in the solar system, not just poorly understood, but lacking even a dominant working theory that survives close examination. Cassini, the spacecraft this time rather than the astronomer, flew past Iapetus in 2007 at relatively close range and sent back detailed images of both the dark terrain and the ridge. The images are remarkable. They did not resolve the mystery of the ridge, but they confirmed it was real, sharp, and stranger up close than it appeared from a distance. 4 centuries after its discovery, Iapetus still has a mountain range running around its equator that nobody can fully explain, sitting on a world that looks like it was painted in 2 colors by a force we still have not identified. Voyager 2 passed Miranda on January 24, 1986, and the images it sent back made planetary scientists genuinely uncertain about what they were looking at. Miranda is one of Uranus's inner moons, small, only about 300 miles across, and sitting nearly 1.8 billion miles from the Sun at the farthest point in Voyager 2's long journey through the outer solar system. The spacecraft had already passed Jupiter and Saturn. It was running on a trajectory that would take it past Uranus and then swing it south and out of the solar system entirely. Miranda was almost an afterthought on that itinerary. The encounter lasted hours. The images it produced have been debated for nearly 4 decades. What those images showed was a surface that looked wrong. Not wrong in the way of a world that had simply been hit many times or slowly eroded. Wrong in a deeper sense. The terrain on Miranda did not fit together. Ancient, heavily cratered plains sat directly next to regions of sharp grooves and ridges that looked completely unlike anything beside them. The boundaries between these zones were abrupt. There was no gradual transition. One type of terrain simply ended and another began, as if pieces of completely different worlds had been pressed together at the seams. Scientists had a name for those grooved and ridged regions. They called them coronae. 3 coronae have been identified and named on Miranda: Arden, Elsinore, and Inverness. Each one is roughly oval in shape, marked by parallel ridges and grooves running across its interior. They look almost like racetrack ovals traced into the surface, surrounded by entirely different terrain. Nothing quite like them exists anywhere else in the solar system. The leading explanation now is that they formed through localized upwelling of warm material from Miranda's interior, bubbling up from below and deforming the surface in distinct regions rather than across the whole moon. The driving force behind that heating was probably ancient tidal stress, back when Miranda's orbit was more elliptical, and the gravitational pull from Uranus was flexing the interior unevenly. The orbit has since settled. The interior has since cooled. What the coronae looked like when they were actively forming, nobody can say with certainty, because we have never seen another one in progress. The cliffs are what stop most people. Verona Rupes is a scarp on Miranda's surface that drops roughly 12 miles straight down. 12 miles. That makes it one of the deepest known cliffs in the solar system, possibly the deepest. On Earth, the tallest sea cliffs reach barely half a mile. The walls of the Grand Canyon are about a mile deep. Verona Rupes would make those features look like curb edges. And because Miranda is so small, its surface gravity is extremely low. only a tiny fraction of what you feel standing on Earth. If you stepped off the edge of Verona Rupes, you would not plummet the way you would on a larger world. You would fall slowly, in a long, quiet arc. The descent would take roughly 12 minutes before the bottom arrived. The impact velocity, when it finally came, would be survivable in theory, though the 12 miles of vertical rock face is another problem entirely. The early explanation for Miranda's chaotic terrain was dramatic. Some researchers proposed that the Moon had been hit hard enough at some point in its history to shatter it completely, and that the pieces had slowly pulled themselves back together under gravity, but in the wrong order, a jigsaw puzzle reassembled without the picture on the box. The idea had a certain appeal. It explained the patchwork quality, the mismatched terrain, the sense that nothing was where it was supposed to be. But the physics did not hold up well under closer examination. Reassembling a shattered moon from scattered fragments would not produce the kind of clean, defined boundaries visible between Miranda's terrain types. It would produce something far messier. The shattering theory has largely been set aside, though not entirely without advocates. The upwelling model replaced it. Under this explanation, Miranda's interior was never uniform. When tidal heating was strongest, certain regions of the interior became warm enough for material to push upward and deform the crust from below. The heating was patchy, uneven, concentrated in specific locations rather than spread across the whole body. Those locations became the coronae. The regions that were never disturbed by upwelling kept their ancient cratered surfaces intact. The result was a moon that looked assembled from mismatched parts, not because it had been broken apart, but because different parts of it had experienced completely different geological histories at different times. What makes Miranda particularly difficult to study is that Voyager 2's flyby in January of 1986 remains the only close observation humanity has ever conducted. No spacecraft has returned. The images from that single encounter, taken at distances and angles that left much of the surface unseen, are still the entire dataset. Roughly half of Miranda was never photographed at useful resolution. The southern hemisphere during the flyby was pointed away from the sun, lost in shadow. What terrain exists there? Whether more coronae are hiding in that darkness, whether Verona Rupes is the deepest feature on the surface, or just the deepest one that happened to be in frame, none of that is known. Miranda has been photographed exactly once, by a spacecraft that flew past it nearly 40 years ago, and the images are still producing arguments. Every large moon in the solar system orbits its planet in the same direction that planet rotates, except one. That exception is Triton, Neptune's largest moon, and the direction it travels is not a minor technical detail. It is the single most important thing about it. When the solar system was forming, everything in the disk of gas and dust around the young sun was spinning the same way. Planets formed from that disk. Their moons formed from smaller disks of material spinning around each planet. The result is that every large moon that grew naturally alongside its planet orbits in the same direction as that planet's rotation. Prograde. It is not a coincidence. It is the predictable outcome of formation from a shared spinning disk. When a moon goes the other way, there is only one explanation. It did not form there. Something put it there after the fact. Triton going backward around Neptune is the clearest possible sign that Neptune captured it from somewhere else entirely. The leading theory is that Triton started out as a Kuiper Belt object. The Kuiper Belt is the vast region of icy bodies beyond Neptune's orbit, the same population that includes Pluto, Eris, and hundreds of thousands of smaller frozen worlds. Triton, at roughly 1,700 miles across, would have been one of the larger members of that population. At some point in the early solar system, it passed close enough to Neptune that the planet's gravity caught it. The mechanics of how that capture worked are not simple. A single object falling toward a planet and passing close to it does not automatically get trapped. It needs to lose energy somehow to drop into orbit, rather than swinging around and flying back out. The most likely mechanism involves a binary companion. Triton may have been traveling through the outer solar system with a partner body when the pair encountered Neptune. The gravitational interaction tore the pair apart, and the energy released in that breakup was enough to bleed off the speed Triton needed to escape. Neptune kept Triton. The companion was flung away. Whatever the exact mechanism, the capture would have been violent. Triton's initial orbit around Neptune was almost certainly highly elongated, a stretched ellipse rather than anything close to circular. An orbit like that is unstable over geological timescales. Tidal forces from Neptune slowly worked on that ellipse, pulling it into a more circular shape. That circularization process takes time, and while it is happening, the tidal stresses on the captured body are enormous. The moon gets squeezed and stretched with every pass around the planet. That squeezing generates heat. For Triton, researchers estimate the tidal heating during orbital circularization could have kept the moon's interior liquid for somewhere between 1 and several billion years. A world that was effectively a captured ball of ice and rock from the outer solar system may have spent a long stretch of its early history as a warm, liquid body deep inside. That is an extraordinary thing to think about. The most geologically chaotic phase of Triton's life happened because it ended up somewhere it was never supposed to be. By the time Voyager 2 flew past in 1989, the only spacecraft ever to visit the Neptune system, Triton had settled into its current nearly circular retrograde orbit. What the cameras sent back was strange. The surface temperature measured around -390 degrees Fahrenheit, making Triton one of the coldest surfaces ever recorded anywhere in the solar system. Neptune sits roughly 30 times farther from the Sun than Earth does. The sunlight reaching Triton is about 900 times weaker than what reaches us. At that distance, almost everything freezes. The surface is covered in nitrogen ice and methane ice and carbon dioxide ice. It looked like a frozen, dead world at the edge of everything. Then Voyager 2 caught something erupting, active geysers. On a surface almost 400 degrees below 0 Fahrenheit, nitrogen was venting from below the surface and shooting up into the thin atmosphere in dark plumes that rose several miles and then spread downwind, leaving dark streaks across the frozen plain below. There were at least 8 active plumes visible in the Voyager images. The mechanism behind them is not internal heat. The Sun, even at that extreme distance, is responsible. Triton's surface is largely transparent nitrogen ice. Sunlight passes through that ice layer and gets absorbed by the darker material just beneath it. The heat builds up, the nitrogen below converts to gas, pressure builds, and eventually it punches through the surface and erupts. The plumes are solar-powered geysers on the coldest surface we have ever measured. The dark streaks they leave can extend for miles downwind across the bright frozen plain. Triton's surface is also young, geologically speaking. there are very few impact craters visible in the Voyager images. On a world that has been sitting in the outer solar system for billions of years, that absence tells you something. Whatever craters formed early in Triton's history have been erased. The surface has been resurfaced repeatedly through some combination of internal heat left over from the capture process and ongoing activity. The exact mechanisms are not well understood, and the data is limited. Voyager 2 gave us most of what we know about Triton in a single flyby that lasted a matter of hours. Part of what makes the Voyager images so difficult to interpret is the terrain itself. A large portion of Triton's surface is covered in a feature that has no equivalent anywhere else in the solar system. Planetary geologists called it cantaloupe terrain because it looks like the skin of a cantaloupe melon. A repeating pattern of rounded dimples and ridges, roughly uniform in size, covering the surface in a pattern that seems almost too regular to be random. The leading explanation involves a process called diaporism, where blobs of warmer, less dense material rise through denser material above them, punching upward like bubbles and deforming the surface into those rounded shapes. It would be driven by the heat left over from Triton's violent orbital history. But that is still a hypothesis. The cantaloupe terrain on Triton has been photographed once by one spacecraft 3.5 decades ago, and the argument over what made it continues. There is a last chapter written into Triton's orbital path, and it is a dramatic one. Retrograde orbits around planets are not stable over extremely long timescales. Tidal interactions between Triton and Neptune are slowly sapping energy from Triton's orbit. Every year, imperceptibly, Triton is getting slightly closer to Neptune. The process is gradual, but 3.6 billion years from now, Triton will have spiraled inward to what is called the Roche limit, the distance at which Neptune's tidal forces become stronger than Triton's own gravity holds itself together. At that point, the Moon will come apart. The material will spread into a ring around Neptune, a ring built from the debris of a world that was never supposed to be there in the first place. A captured wanderer from the outer solar system finally returned to pieces. Triton does not belong where it is. Its orbit is slowly failing, and in a few billion years it will break apart and become the most spectacular ring system in the outer solar system. Hyperion looks like someone took a moon and punched holes in it. Not small holes. Deep, steep-walled craters punched into an already irregular, lumpy surface, separated by thin, sharp ridges that look nothing like the rounded crater rims you see on the Moon or Mars. The overall shape is not even close to spherical. Hyperion stretches roughly 170 miles at its longest dimension and considerably less in the other directions. It is a battered, asymmetrical chunk of something, and it looks wrong in a way that is hard to pin down until you realize what you are actually looking at. The texture is the first thing that registers. Scientists who studied Cassini's close images of Hyperion described it as sponge-like, and that is not an exaggeration. The craters do not blend into each other the way they do on heavily bombarded worlds like Callisto, where overlapping impacts eventually smooth things out into a kind of rough but continuous terrain. On Hyperion, each crater stays sharply defined. The walls stay steep, the floors stay deep. This happens because of what Hyperion is made of, or more precisely, what it is not made of. Its density is unusually low, somewhere around 40% empty space. The interior is porous, probably riddled with voids. When something hits Hyperion, The material does not splash outward across the surface the way it would on a denser world. Instead, the impact compresses and excavates straight down. The debris that would normally scatter and fill nearby terrain gets absorbed into the porous structure. The result is a surface covered in holes that stay exactly where they formed, sharp and isolated, never filling in. The floors of those craters are dark and reddish. The same kind of organic material shows up on moons and small bodies throughout the outer solar system, the product of ultraviolet light and charged particles processing simple carbon-bearing compounds over billions of years. On Hyperion, these dark deposits settle into the lowest points of the terrain, coating the crater floors, while the higher ridges stay slightly brighter. The contrast gives the surface an almost hand-painted quality, dark pits separated by lighter walls, the sponge pattern made even more visible. But the shape and the texture are not the strangest thing about Hyperion. The strangest thing is what it is doing as it moves. Most moons in the solar system are tidally locked. Gravity from the planet they orbit gradually slows their rotation and fixes them so the same face always points toward the planet. Our moon does this. Titan does this. Virtually every moon of any significant size does this, given enough time. The process is slow but inexorable, and for most moons, billions of years has been more than enough time to complete it. Hyperion never locked. Its rotation is genuinely chaotic, in the precise mathematical sense of the word. Chaotic motion is not just complicated or irregular. It means the system is so sensitive to its initial conditions that even in theory, even with perfect knowledge of where Hyperion is and how fast it is spinning right now, you cannot calculate how it will be oriented weeks from now. Small uncertainties in the current state grow exponentially. The future becomes unpredictable, not because we lack information, but because the physics itself amplifies any uncertainty without limit. The culprit is Titan. Hyperion orbits Saturn in a resonance with Titan, completing 3 orbits for every 4 that Titan completes. This keeps the 2 moons in a repeating gravitational relationship, and Titan is large enough to give Hyperion a significant tug at regular intervals. Saturn is pulling on Hyperion as well. The combination of these 2 gravitational influences, acting on a body that is already asymmetrical and irregularly shaped, produces a torque that never settles into a stable pattern. Hyperion tumbles. It is always tumbling, end over end in a pattern that shifts and never repeats. When Cassini made multiple passes of Hyperion over the years, each flyby showed the moon oriented completely differently. This was not a surprise by then, because astronomers had already worked out theoretically that Hyperion's rotation should be chaotic well before Cassini arrived at Saturn. But seeing it confirmed in the images, a different face each time, craters that were in shadow now in sunlight, the whole body presenting itself in a new configuration with every encounter, is something else entirely. It is worth pausing on what this means practically. If you were standing on Hyperion, the direction of Saturn in the sky would drift unpredictably. The sun would not rise and set on any reliable schedule. There would be no way to construct a calendar based on where anything appears overhead, because nothing appears in the same place twice. The orientation of the entire world would be genuinely unknown from one month to the next. Hyperion is almost certainly not an original object. Something this porous, this irregular, this physically strange, did not form this way from scratch. The leading interpretation is that it is a remnant, a fragment left behind after a much larger body was struck hard enough to break apart. The original object is gone. What remains is this porous, tumbling, sponge-shaped piece of wreckage, still orbiting Saturn billions of years after whatever destroyed its parent. It is probably the surviving fragment of a much larger body that no longer exists, tumbling through its orbit in a way that makes it impossible to predict how it will be oriented on any given day. When the Voyager spacecraft sent back the first detailed images of Mimas in 1980, scientists noticed something immediately. The moon looked like a weapon from a movie that had not yet been released when the mission was planned. Star Wars came out in 1977. Voyager launched the same year. By the time the images arrived, everyone already knew what the Death Star looked like. And here, orbiting Saturn, was essentially the same object, a nearly spherical grey body with one enormous circular crater dominating an entire hemisphere, complete with a central peak rising from the middle like a bullseye. Nobody had designed it that way. Mimas had been sitting there for billions of years, long before George Lucas put pen to paper. The crater is called Herschel, named after the astronomer William Herschel, who discovered Mimas in 1789. It is roughly 80 miles across on a moon that is only about 250 miles in diameter. That ratio is extraordinary. Herschel takes up nearly a third of the moon's entire face. The walls drop about 6 miles to the crater floor. The central peak rises nearly 4 miles from that floor, which puts it in roughly the same height range as Mount Everest, measured from sea level. The impact that formed it came close to ending Mimas entirely. Scientists who have modeled the collision estimate that only a slightly larger impactor would have split the moon apart. It held together, but barely. You can see the evidence on the other side. Directly opposite Herschel, on Mimas's far hemisphere, the terrain becomes chaotic. The surface is broken and jumbled in a way that matches nothing else on the moon. The leading explanation is that when the impactor hit, the shock waves traveled through Mimas's body and converged on the opposite side with enough focused energy to fracture the surface from below. The same effect has been observed on other bodies. Mercury has similar chaotic terrain directly opposite its Caloris basin. On a small, rigid body like Mimas, those focused waves had nowhere to go. They simply tore the surface apart on the far side, while the rest of the moon survived. For decades, that was the story of Mimas. It looked like the Death Star. It had an almost catastrophic crater, and beyond that, it appeared to be a fairly simple, geologically dead chunk of ice and rock. It was cold, it was inert, and compared to Europa or Enceladus, it seemed to have nothing more to say. Then Cassini changed that. The Cassini spacecraft carried an instrument that could map surface temperatures across a body as it orbited. When researchers turned it toward Mimas and mapped the thermal signature, they expected a straightforward result. A cold moon warmed slightly on the sunlit side, cooling gradually toward the terminator and the dark hemisphere. That is how inert, icy bodies behave. What the data showed instead was something that looked, with only minor exaggeration, like the video game character Pac-Man. A warm crescent shape on the leading hemisphere, with the warm area cutting off sharply in a pattern that made no physical sense for a simple frozen world. The Cassini team published the finding in 2010. Nobody had a clean explanation. The most widely accepted interpretation involves surface texture. Most of Mimas appears to be covered in an extremely fine, porous layer of ice particles, almost like fresh powdery snow, but sparser. Material like this heats up almost instantly when sunlight hits it and loses that heat just as fast when the sun moves away. Certain regions, possibly where the ice is more compacted or structured differently, behave more like solid ice, which holds temperature longer and creates a different thermal pattern when mapped. The boundary between these regions, running across the face of Mimas, traces out that Pac-Man shape. The surface is not uniform in ways that are just beginning to be understood. That explanation is reasonable and fits the data well enough that many researchers accept it. But another possibility has been gaining quiet attention. A small number of studies have proposed that Mimas may have a subsurface liquid ocean, buried beneath an ice shell thick enough that it leaves almost no obvious trace on the surface. The evidence is far thinner than for Europa or Enceladus. There are no geysers, no cracked terrain, no magnetic field signature pointing toward a salty conductor underneath. But the thermal anomaly is real, and some models suggest an interior ocean could produce subtle surface effects consistent with what Cassini observed. The debate is unresolved. What is not in debate is the other significant thing Mimas does. Its orbital period around Saturn is almost exactly 1/2 of the orbital period of the ring particles sitting at a specific gap in Saturn's famous ring system. This 2-to-1 resonance means that any particle trying to maintain an orbit in that zone gets a gravitational nudge from Mimas at regular intervals, always in the same direction, building up until the particle is pushed out. The result is the Cassini division, the dark gap roughly 3,000 miles wide that runs through Saturn's rings and is visible through even a modest telescope on Earth. Mimas carved it out through nothing more than showing up at the same place repeatedly over millions of years. Mimas is the moon that looks like a movie prop, but it is also the object creating the most prominent gap in Saturn's rings, and it may have an ocean, and frankly, none of that was supposed to be true for something this small. Asaph Hall had been searching for Martian moons for years and had nearly given up when his wife told him to try one more night. That was August 1877. He went back to the telescope. Within days, he found 2 moons orbiting Mars, Deimos on August 12th, Phobos on August 18th. Both small, both dark, both strange. Nobody had seen them before despite centuries of watching Mars, because they are extraordinarily difficult to spot against the glare of the planet itself. Hall's wife, Angeline, had pushed him to continue when he was ready to abandon the search entirely. Her name deserves to be in the story. Without that conversation, the discovery might have waited years longer. Phobos is the inner moon, and it is not large. Roughly 17 miles across at its widest, lumpy and irregular in shape, more like a battered potato than anything you would draw if someone asked you to sketch a moon. Its surface is heavily cratered and blanketed under a thick layer of powdery regolith, a loose, dusty coating that has built up over billions of years of micrometeorite impacts, grinding the surface down into fine material. But the stranger thing about Phobos is not what it looks like. It is where it is and how fast it moves. Phobos orbits Mars at an altitude of only about 3,700 miles. That is extraordinarily close. Our own moon orbits Earth from roughly 239,000 miles out. Phobos is practically skimming Mars's upper atmosphere by comparison, and because it orbits so close, it moves fast. One full orbit takes just under 8 hours. Mars itself rotates once every 24 hours. Phobos laps it. The Moon completes 3 full orbits while Mars turns once. The result of this is something that exists nowhere else in the solar system. From the surface of Mars, Phobos rises in the west and sets in the east. Every other moon of every other planet rises in the east. Phobos alone goes the wrong way, not because its orbit is retrograde, but because it is moving faster than the planet beneath it is turning. The surface of Phobos tells its own violent story. The most prominent feature is Stickney Crater, a 6-mile-wide impact scar sitting on a moon that is only 17 miles across. That impact was catastrophic. Something hit Phobos hard enough to excavate a crater 1/3 the width of the entire body without shattering it completely. The shock would have sent fractures running through the moon in every direction. And there are fractures. Long parallel grooves stretch across the surface of Phobos, radiating outward from Stickney, and the obvious explanation is that they are scars left by the collision. But some researchers are not convinced. An alternative interpretation is that these grooves are not damage from the Stickney impact at all. They may be structural failures caused by something else entirely. The slow gravitational squeezing of Phobos as its orbit tightens. Because Phobos's orbit is tightening, Mars is pulling Phobos inward at a rate of about 6 feet per year. That sounds small. Over a human lifetime, it is nothing. But across geological time, 6 feet per year adds up. In roughly 50 million years, Phobos will get close enough to Mars that one of 2 things will happen. Either it will crash into the planet's surface in an impact visible across the entire solar system, or it will cross the Roche limit, the distance at which tidal forces exceed the gravity holding a body together, and it will be pulled apart, shredded into fragments. Those fragments would spread into a ring around Mars, something Mars has never had. A planet that currently has 2 moons will have, in geological terms relatively soon, either a crater or a ring. The grooves on Phobos, if that alternative theory is right, are the first visible signs of what is coming. The moon is already beginning to crack under the stress of its own approaching destruction. Deimos is a different story entirely. Smaller than Phobos, only about 9 miles across, Deimos orbits much farther out. Its surface is smoother. Where Phobos is rough and heavily scarred, Deimos looks almost soft. Craters that should be sharp-edged have been filled and blurred by fine material settling into them over time. It is a quieter-looking world, and its fate is quieter too. Deimos orbits just outside the distance at which Mars's tidal forces would drag it inward. Instead, those tidal forces push it outward, very slowly, in the same way that our moon is slowly drifting away from Earth. Deimos is not falling toward Mars. It is leaving. The drift is far slower than Phobos's inward spiral. Across a human lifetime, it is effectively nothing. But the direction is clear. Deimos is moving away from Mars. Eventually, far in the future, it may drift far enough that Mars can no longer hold it. 2 moons of the same planet, one falling, one drifting. Side by side in orbit right now, both discovered on consecutive nights by the same exhausted astronomer in 1877. Both heading in opposite directions over the long arc of time. For most of the time since their discovery, the assumption was that Phobos and Deimos were captured asteroids. Their small size, dark surfaces, and irregular shapes looked similar to objects in the outer asteroid belt. The capture hypothesis made a kind of intuitive sense. But there are problems with it. Capturing an asteroid into a nearly circular orbit around a planet is surprisingly difficult to do without some mechanism to bleed off excess velocity. Captured objects tend to arrive in elongated, tilted orbits, not the nearly circular equatorial orbits that both Phobos and Deimos follow. The current leading hypothesis is something different. The idea gaining support now is that Phobos and Deimos formed from debris thrown into orbit by a giant impact on Mars, similar in principle to how Earth's moon is thought to have formed from the debris of a collision with a Mars-sized body billions of years ago. This would explain the near-circular orbits and the alignment with Mars's equatorial plane far more naturally than any capture scenario does. The surface composition does not perfectly match this model either, so the debate continues. What is clear is that these two moons are not what they appear to be, and their origin is still not settled. One of Mars's moons is falling toward it, and the other is slowly drifting away, and in 50 million years, Mars will have neither. Charon is half the size of Pluto, and that one fact changes everything about how the system works. Most moons are small. Our own moon feels enormous to us. It fills the sky, it drives the tides, it has shaped calendars and myths for all of recorded history. But in terms of mass, the moon is about 1.2% of Earth. It is a footnote sitting next to a planet. Charon is not a footnote. Charon is roughly half Pluto's diameter and holds about 12% of Pluto's mass. No other moon in the solar system comes close to that ratio. Not one. When you try to find a comparison, you cannot find one, because nothing like this system exists anywhere else we have looked. The consequence of that mass ratio is a gravitational one, and it is strange. When a small object orbits a much larger one, the center of gravity of the whole system, the barycenter, sits deep inside the larger body. Earth's barycenter with the moon sits well within Earth's interior. The moon orbits around a point inside our planet. That is the normal arrangement. Pluto and Charon do not have a normal arrangement. Because Charon is so massive relative to Pluto, the barycenter of their system sits out in open space between the two bodies. Neither Pluto nor Charon orbits the other. Both of them orbit a point that floats in the space between them. They are locked face to face, each keeping the same hemisphere pointed permanently toward the other, circling together around a shared gravitatis zonal center that neither of them contains. This is not a planet with a moon. This is a double world. Some planetary scientists will tell you the Pluto-Charon system is the only confirmed double dwarf planet in the solar system. They are not wrong to call it that. The formal definitions get complicated, but the physics is clear. These two bodies move together the way partners move, not the way a host moves with a satellite. 6 days and 9 hours is how long one full orbit takes. In that time, Pluto and Charon complete one full turn around each other, locked in the same face-to-face orientation they have maintained for billions of years. For a long time, that was essentially all we knew. Charon was discovered in 1978 by astronomer James Christie, who noticed that images of Pluto showed a slight elongation that moved over time. The elongation was Charon, too small and too close to separate cleanly with the telescopes of the era. For decades, Charon was a blur on the edge of Pluto in even the best images. Hubble improved that picture somewhat, but only enough to confirm the basic geometry. The surface of Charon was unknown. What lay underneath that small, distant, icy exterior was a complete mystery. Then New Horizons arrived in July 2015. The spacecraft had been traveling for 9.5 years. It crossed the orbit of Neptune before it reached Pluto. When it finally made its closest approach and the data began coming back, the surface of Charon turned out to be nothing like what most researchers had anticipated. There were mountains. There was evidence of geological activity far more recent than anyone had predicted for a body this cold and this small. And running across a significant portion of the visible surface was a canyon system that stopped scientists cold when they first processed the images. The canyon is enormous, roughly 1,000 miles long and up to 6 miles deep in places. For scale, the Grand Canyon is 277 miles long and a little over a mile deep at its deepest. Charon's canyon system dwarfs it entirely. In proportion to the body it sits on, there is nothing like it on Earth. The leading explanation is that Charon once had a subsurface ocean that froze. Water expands when it freezes. If the interior of Charon was liquid and then solidified, the expansion would have cracked and stretched the surface, pulling it apart in exactly the kind of long, rifted canyon system that New Horizons photographed. A moon that may have had an interior ocean, now frozen, wearing the evidence of that freezing as a scar across its surface. The North Pole is the other thing. In New Horizons images, Charon's North Polar region is capped in a deep reddish-brown material, unlike the rest of the surface. Scientists named it Mordor Macula. The color and composition of this material match tholins, complex organic molecules built from simpler compounds when they are exposed to ultraviolet radiation and charged particles. This happens elsewhere in the solar system. What makes Charon's North Pole different is the source of the raw material. Pluto has an atmosphere. It is thin and seasonal, swelling as Pluto moves closer to the Sun in its long elliptical orbit and collapsing back as it recedes. But it is real. Methane from Pluto's atmosphere escapes into space, and some fraction of that material travels across the gap between the two worlds and reaches Charon. At the poles, where temperatures drop low enough during Charon's long winter, that methane freezes onto the surface. When sunlight returns, the methane itself may escape, but the heavier organic molecules processed from it by radiation do not. They stay, they accumulate, they build up over millions of years into the dark reddish cap that New Horizons photographed. Pluto is painting its own moon. The atmosphere of one world is leaving a permanent mark on the surface of another. The distance between them is only about 12,000 miles, close enough that material genuinely crosses from one to the other on timescales that matter geologically. New Horizons flew through the Pluto system in a matter of hours. It was moving too fast to slow down, and there was no second spacecraft waiting to take over. Everything we know about Charon's canyons, its frozen ocean hypothesis, its strange red pole, all of it comes from one fleeting encounter nearly a decade ago. Pluto's atmosphere is actively painting the north pole of its moon in organic compounds, and we have only ever seen any of this once. The moon is 400 times smaller than the Sun and 400 times closer to Earth than the Sun, which means from our surface they appear almost exactly the same size in the sky, and this is almost certainly a coincidence. Nobody designed this. No force in orbital mechanics requires it. The moon just happens to sit at the right distance to fit almost perfectly over the solar disk, and that accident has shaped human history in ways most people never think about. During a total solar eclipse, when the moon slides exactly over the sun, the outer atmosphere of the sun, the corona, becomes visible from Earth's surface. That thin white halo of plasma, normally invisible against the brightness of the solar disk, suddenly appears around the edges. Victorian astronomers used these brief windows to study it. In 1868, during a total eclipse visible from India, astronomers detected a spectral line in the sun's atmosphere that did not match any element known on Earth. They called it helium, after Helios, the Greek sun god. It was the first element discovered in space before it was found on Earth. That discovery came from the coincidence of the moon being exactly the right apparent size. The moon itself is strange in ways that go beyond where it sits. Our moon is large. Not large in absolute terms, but large relative to its host planet in a way that is nearly unique in the solar system. Earth's moon is about 1/4 the diameter of Earth and about 1.2% of its mass. That ratio is enormous compared to the moons of other rocky planets. Mars has 2 moons, both tiny. Mercury and Venus have none. For a planet the size of Earth to have a moon this substantial, something unusual had to happen. The leading explanation is called the giant impact hypothesis. About 4.5 billion years ago, when Earth was still young, a body roughly the size of Mars struck the early Earth at an oblique angle. Astronomers call this impactor Theia. The collision was not a direct hit. It was more like a glancing blow, energetic enough to vaporize and eject an enormous quantity of material from Earth's outer layers into orbit. That debris, a ring of rock and vapor circling the young Earth, gradually clumped together under its own gravity and formed the moon. The whole process probably took only a few thousand years in geological terms, almost instant. The giant impact hypothesis explains several things that were otherwise difficult to account for. The moon's composition is strikingly similar to Earth's mantle rock. Not exactly the same, but close enough to suggest they share a common source. The moon also has almost no iron core. Earth, by contrast, has a substantial iron core that generates its magnetic field. The explanation is that by the time Theia hit the early Earth, the iron in both bodies had already sunk toward their respective cores through a process called differentiation. The collision excavated mainly the rocky outer material, leaving the iron behind. The moon that formed from that debris was built mostly from silicate rock with almost no iron mixed in. The moon always shows the same face to Earth. The far side exists and has been photographed extensively since the Soviet Luna 3 mission in 1959. But from Earth's surface, you will never see it. This is called tidal locking, and it happened gradually. Early in the moon's history, it rotated freely. But Earth's gravity exerted a tidal force on the moon, creating a slight bulge on the moon's near side that acted as a brake. Over millions of years, that friction slowed the moon's rotation until it matched its orbital period exactly. One rotation per orbit, the same face, always facing Earth. The moon is also slowly leaving. Every year, the moon moves about 1.5 inches farther from Earth. That sounds trivial. Over a human lifetime, it amounts to a few feet. But project it backwards, and the numbers become dramatic. Early in Earth's history, the moon was much closer. Some estimates put it at roughly 10 times closer than it is today, though the exact figure is uncertain. At that distance, tidal forces would have been orders of magnitude stronger. the oceans would have surged in tides far larger than anything we experience now. The friction from those enormous tides was also acting on Earth's rotation, slowing it down. A day on early Earth was somewhere around 6 hours. The Moon has been gradually breaking Earth's spin for billions of years. The 24-hour day is partly the Moon's doing. That recession is measurable today. The Apollo missions left retroreflectors on the lunar surface. Observatories on Earth fire laser pulses at them and time the return. The distance is known to within a few centimeters. The Moon is unambiguously drifting away, and the measurement is direct. The strangest thing about Earth's Moon, though, may be what it does for the planet quietly and continuously, without anyone noticing. Earth's axial tilt is currently about 23.4 degrees. That tilt is what produces the seasons. It stays relatively stable over long periods, varying only slightly over cycles of tens of thousands of years. The reason it stays stable is the Moon. The Moon's gravitational presence damps out the wobbles that would otherwise develop in Earth's tilt over millions of years. Mars, which has no large moon, has an axial tilt that has varied enormously over geological time, swinging through a range that may extend from nearly 0 degrees to over 40 degrees. A planet tilting that dramatically changes its climate in extreme ways. Ice ages deepen and shift. Seasons become unrecognizable. The conditions for stable ecosystems over hundreds of millions of years become much harder to maintain. Earth's axial tilt has been held roughly in place by the Moon for long enough that complex life could develop and persist. That stability is not guaranteed. It is a consequence of having a large moon in the right place. Without the Moon holding Earth's axial tilt stable, the planet's climate would have lurched through changes severe enough that complex life might never have gotten a foothold, and you would not be listening to this. Inside the orbit of Io, deep within Jupiter's radiation belts, there are 4 small moons that most people have never heard of, while Io, Europa, Ganymede, Callisto get the attention, the oceans, the volcanoes, the magnetic fields. There is an inner tier of worlds sitting far closer to Jupiter. In a region of space so hostile that sending a spacecraft to orbit any of them would be a short mission. The radiation environment near Jupiter's equatorial plane, at the distances these moons occupy, is intense enough to damage electronics and degrade hardware at a rate that makes long-term observation essentially impossible. These are not places where spacecraft linger. The 4 moons are Metis, Adrastea, Amalthea, and Thebe, arranged in order outward from Jupiter. Metis and Adrastea are tiny, both under 30 miles across, orbit so close to Jupiter that they are actually inside the planet's synchronous rotation radius, meaning they orbit faster than Jupiter spins. Thebe sits farther out, beyond Amalthea, irregularly shaped like the rest, cratered and dark. But Amalthea is the largest of the group and the one that has produced the most surprises. Amalthea is about 168 miles long and 96 miles wide. It is not round. It looks something like a battered potato, elongated and lumpy, covered in craters. With its long axis pointing permanently toward Jupiter because tidal forces locked it in place long ago. It orbits Jupiter in roughly 12 hours, traveling inside the path of Io. That already sits deep inside one of the harshest radiation environments in the solar system. Amalthea sits closer still. When the Galileo spacecraft swung past Amalthea in November 2002, one of its final maneuvers before its mission ended, the data it returned contained something unexpected. Amalthea is putting out more heat than it receives from the Sun. For a small, geologically dead rock at that distance from the Sun, this should not happen. The Sun is simply too far away. Amalthea is simply too small to have retained any meaningful internal heat from its formation. Something else is warming it. The leading explanation involves Jupiter's magnetic field. Jupiter generates the most powerful planetary magnetic field in the solar system, and Amalthea moves through it constantly. As a conducting body moving through a magnetic field, electrical currents are induced inside the Moon. Those currents generate heat. Amalthea is not being heated from inside, and it is not being heated by the Sun. It is being heated by the electromagnetic environment it is flying through. The Moon is, in a practical sense, being cooked by Jupiter's magnetosphere from the outside in. Then there is the color. Amalthea is one of the reddest objects in the entire solar system. When Voyager 1 flew past in 1979 and returned the first close images, scientists noted immediately how strikingly red it was. The source of that color is almost certainly Io. Io's volcanic eruptions throw enormous quantities of sulfur compounds into space. Much of that material eventually coats the surfaces of moons orbiting in the same region. Amalthea sits inside Io's orbit, but sulfur ejected from Io's plumes spreads outward and inward, settling onto nearby surfaces. Amalthea has been accumulating this material for a very long time. Io is, in effect, spray painting everything nearby in sulfur compounds. Amalthea is close enough to have received a thorough coating. The inner moons also have a structural role in the Jupiter system that has nothing to do with their own geology. Jupiter has a faint ring system, nothing like Saturn's, far too dim to see with the naked eye, but real and measurable. The source of that ring material is Amalthea, Thebe, Metis, and Adrastea. Micrometeorites strike these moons constantly, and each impact kicks dust and debris off the surface. That material drifts into orbit around Jupiter and spreads into the thin ring structures that Voyager 1 first detected in 1979. The rings exist because the moons are there and are being slowly eroded by impacts. Without them, there would be no rings. What is striking about all of this is how little we actually know. Amalthea has been photographed by Voyager 1, Voyager 2, and Galileo. The Galileo flyby in 2002 remains the closest encounter any spacecraft has made. After that, the mission ended deliberately. The spacecraft was crashed into Jupiter to avoid any risk of contaminating Europa. No mission since has gone back. The radiation environment makes dedicated study difficult to justify against other priorities. The moons are small enough that they do not generate the same scientific urgency as the Galilean worlds. They orbit in a zone that destroys the tools we would need to study them. Amalthea is being heated by electromagnetic induction, spray-painted by sulfur from Io. It sits inside a radiation zone that would destroy most space. Craft sent to study it closely, and it has barely been looked at. Saturn has a ring that is invisible to the naked eye, nearly invisible to most telescopes, and wider than the full moon appears from Earth. And it comes from a moon most people have never heard of. Phoebe is about 135 miles across. It orbits Saturn at an enormous distance, far beyond the regular moon system, in a direction opposite to Saturn's rotation. That last detail is the critical one. Every moon that formed alongside Saturn from the same spinning disk of material orbits in the same direction Saturn rotates. Phoebe goes the other way. That retrograde orbit is not a quirk, it is a signature. It means Phoebe did not form here. Saturn captured it from somewhere else. The Cassini spacecraft flew past Phoebe in June of 2004, just before entering Saturn orbit. It was the closest look humanity had ever gotten, and the images were striking. Phoebe is dark and heavily cratered, irregular in shape, nothing like the smooth, icy inner moons of Saturn. It looks ancient. The surface is covered in craters of every size, some deep enough that the material blasted out of them exposed what was underneath. And what was underneath the dark outer layer was bright, icy. The dark surface of Phoebe is a crust, a skin of organic material sitting over an interior that is largely composed of ice. That combination told researchers something important. The composition of Phoebe does not match Saturn's regular moons at all. It matches the objects in the Kuiper Belt, the vast reservoir of icy bodies beyond Neptune that includes Pluto, Eris, and thousands of other worlds. Phoebe appears to be one of those objects. At some point in the solar system's history, it passed close enough to Saturn to be gravitationally captured and locked into orbit. Saturn reached out across an enormous distance and grabbed a piece of the outer solar system. This is not a clean or simple process. Capture requires the incoming body to lose enough energy during the encounter to become bound. That usually involves a close gravitational interaction, a third body, or some combination that bleeds off the speed an object needs to escape. Whatever the mechanism, Phoebe ended up in a wide, tilted, retrograde orbit far from Saturn, where it has been ever since. It never became part of the regular moon system. It remained alien, a small frozen world from the edge of things, orbiting a planet it was never born near. For decades, Phoebe was considered an interesting oddity. Then, in 2009, astronomers found something that changed how Phoebe fits into the broader Saturn system. Using the Spitzer Space Telescope, a team detected an enormous diffuse ring surrounding Saturn at roughly the distance of Phoebe's orbit. It is not like Saturn's bright inner rings. There are no sharp edges, no visible structure. It is a vast, faint cloud of dust and particles spread across a region so large it is almost impossible to describe in familiar terms. If it were somehow visible to the naked eye, it would appear in the sky as a band twice the width of the full moon. The ring is tilted relative to Saturn's other rings, which orbit roughly in Saturn's equatorial plane. The Phoebe ring sits at a different angle, matching Phoebe's own orbital inclination. That tilt, along with its location, pointed directly at the source. Micrometeorites constantly hit Phoebe. Each impact kicks small amounts of material off the surface and into space. Over millions of years, this slow, steady loss of dust has built up a ring tracing Phoebe's own path around Saturn. That dust does not just sit there, it drifts inward, spiraling slowly towards Saturn under the influence of solar radiation pressure and gravitational forces. As it moves inward, it intersects the orbit of Iapetus. And this is where the connection becomes something more than coincidence. Iapetus, Saturn's two-toned moon, has one hemisphere almost entirely black and one almost entirely white. The dark material has puzzled researchers for centuries. The Phoebe ring explains where it came from. Dust spiraling inward from Phoebe collects on the leading hemisphere of Iapetus as Iapetus sweeps through its orbit. Two moons with no obvious relationship turn out to be connected by a ring invisible to every telescope for the first 338 years after Iapetus was discovered. Phoebe is not alone in being a captured body. Saturn has dozens of smaller, irregular moons beyond its regular system, most of them just a few miles across, most of them discovered only in the last 20 years as telescope technology improved. Jupiter has more than 90 known moons now, and the vast majority of them are small, irregular bodies in distant, tilted, often retrograde orbits. Uranus has irregular moons. Neptune has Triton, which is just a very large version of the same story. The giant planets are surrounded by swarms of captured objects, small bodies from the outer solar system that wandered too close and never left. Most of them have never been visited by a spacecraft. Most of them have no names that anyone outside a specialist community would recognize. They are dark and small and far away, and they have been orbiting their captured paths for billions of years. Phoebe is one of dozens of captured outer moons at each of the giant planets, each of them a small alien body from the outer solar system held in permanent gravitational captivity. Look at enough moons and a pattern emerges that the textbooks about solar system formation did not quite predict. The standard story is a clean one. A disk of gas and dust surrounds a young star. Gravity pulls material together. Clumps form. Clumps collide. Planets grow. Moons form from the leftover debris orbiting those planets, spinning in the same direction, settled into neat circular paths, everything calm and orderly. That is the version that fits neatly into diagrams. Then you go look at the actual moons. Triton orbits Neptune backward. Charon is so massive relative to Pluto that the two objects orbit a point in empty space between them. Miranda looks like it was broken into pieces and put back together by someone who lost the instructions. Iapetus is painted jet black on one side and brilliant white on the other, and the best explanation involves a runaway feedback loop that took hundreds of millions of years to complete. These are not edge cases. These are some of the most significant moons in the solar system, and none of them fit the quiet, orderly picture. What they fit instead is chaos. Specifically, they fit the kind of chaos that planetary scientists now believe defined the early solar system for its first several 100 million years. Two models try to describe this period. The Grand Tack hypothesis proposes that Jupiter formed and then migrated inward toward the Sun, nearly reaching the orbit of Mars before Saturn's gravity pulled it back outward. This inward and outward migration would have scattered enormous numbers of smaller bodies. Asteroids, comets, proto-moons, Kuiper Belt objects. All of them were flung across the solar system during this reshuffling. Some were ejected entirely. Others were thrown into new orbits. Some were captured. The Nice model describes a later episode. After the planets settled into roughly their current positions, a period of gravitational instability caused Saturn, Uranus, and Neptune to shift outward. This triggered what is called the Late Heavy Bombardment, a period roughly 4 billion years ago when the inner solar system was pelted with impactors. The Moon's surface, pockmarked with ancient craters, carries the record of that bombardment. So does Callisto. So does every heavily cratered body we have visited. The timing of those craters tells us something real happened to destabilize the solar system after the initial formation period was already complete. The irregular moons are the clearest evidence of this violent history. Every giant planet has them. Jupiter has more than 90 known moons, and the vast majority are small irregular bodies orbiting at enormous distances in tilted, elongated, often retrograde paths. Saturn has a similar population. So do Uranus and Neptune. These moons do not belong to the neat inner system of large, tidally locked regular moons. They move like captured prisoners. Their orbits make no sense if they formed alongside their planets. They make complete sense if they were scattered inward from the outer solar system during a period of planetary migration and then gravitationally trapped. Phoebe at Saturn, the irregular moons clustering in distant retrograde groups at Jupiter. These are fragments of the early Aute, our solar system, brought to where they are now by a history that was anything but gentle. But the story the moons tell is not only about violence, it is also about water. The icy moons of Jupiter and Saturn, Europa, Ganymede, Callisto, Enceladus, Titan, have collectively forced a rethinking of one of the most basic assumptions in the search for life. For decades, the habitable zone meant one thing: the narrow band around a star where liquid water could exist on a planetary surface. Too close, and it boils away. Too far, and it freezes. Earth sits inside that band. Mars is near the edge. Jupiter is far outside it. And yet Europa has a liquid ocean. Enceladus has a warm, salty ocean with active seafloor vents. Titan has a chemically rich environment with organic molecules raining out of the sky. These worlds are at the orbit of Jupiter and Saturn. By the classical definition, they have no business being anything other than frozen solid. The reason they are not frozen comes down to tidal heating. When a moon orbits a massive planet and is being pulled by the gravity of neighboring moons as well, the resulting flexing generates heat from the inside. This heat has nothing to do with the star. It does not care how far the system is from its sun. It is mechanical energy, converted to thermal energy through the constant squeezing and releasing of the moon's interior. This means that any moon around any giant planet in any solar system, at almost any distance from any star, could potentially maintain a liquid water ocean if the orbital geometry is right. The implications are significant. If subsurface oceans exist around Jupiter and Saturn in our own solar system, and there is strong evidence that several of them do, then this is probably not unusual. Most solar systems appear to have giant planets. Giant planets have moons. Moons around giant planets experience tidal heating. The universe may be full of subsurface oceans sitting beneath ice shells, warmed from below, insulated from above, completely invisible from the outside. The classical habitable zone turns out to describe only one type of habitable environment. Tidal heating describes another, and it operates across a far larger volume of space. This is not a minor adjustment to how planetary scientists think about life in the universe. It is a fundamental expansion. The number of potentially habitable environments goes from a narrow ring around each star to something that includes the entire population of moons around giant planets everywhere. In our solar system alone, the count of worlds with confirmed or strongly suspected liquid water now sits at 4 or 5, depending on how you weigh the evidence for Callisto and Mimas. A generation ago, that number was 1. The search for life in the solar system has quietly shifted over the past 2 decades, away from planets and toward the moons orbiting them. Right now, at this moment, 2 spacecraft are traveling toward the Jupiter system specifically to study its icy moons. Europa Clipper launched in October 2024. JUICE, the Jupiter Icy Moons Explorer, built by the European Space Agency, launched in 2023. They are heading to the same neighborhood by different routes, carrying different instruments, asking slightly different questions. Both of them will arrive in the early 2030s. What they find there may be the most consequential scientific result of this century. Europa Clipper will not orbit Europa. The radiation environment around Jupiter is brutal enough that a spacecraft parked in orbit around Europa would be destroyed within months. Instead, it will orbit Jupiter and conduct nearly 50 close flybys of Europa, dipping in, collecting data, and pulling back out before the radiation accumulates to dangerous levels. Each pass will build a more detailed picture of what is underneath the ice. The magnetic field readings will tell scientists how thick the ice shell actually is. Infrared instruments will map the surface temperature, looking for spots where warm water from below might be pushing closer to the surface. If there are active plumes on Europa, water erupting the way Enceladus erupts, Europa Clipper will fly through them and taste what comes out. Enceladus gave us molecular hydrogen and complex organics through exactly this kind of encounter. Europa could give us something more specific, something harder to explain without biology. Nobody is saying that is likely, but the instruments are capable of detecting it, and that is a new thing in the history of this search. JUICE takes a different path. Its primary target is Ganymede. It will eventually enter orbit around Ganymede, making it the first spacecraft to orbit a moon other than our own. Along the way, it will conduct multiple flybys of Callisto and Europa. Ganymede's magnetic field, its internal ocean, the strange grooved terrain that nobody has fully explained. JUICE will spend years working through these problems from close range. Then there is Dragonfly. This one is different in kind, not just in scale. Dragonfly is a rotorcraft lander, nuclear-powered, scheduled to arrive at Titan in the mid-2030s. It will fly, not roll across the surface the way a rover does, covering a few miles over several years. It will lift off, navigate through Titan's thick atmosphere, and land at a new site. Then do it again. Over the course of its mission, it could cover more than 100 miles of Titan's surface, sampling the chemistry at riverbeds, dune fields, and crater floors, where liquid water briefly existed after ancient impacts. The organic chemistry building up in Titan's environment is not simple. Tholins, the complex molecules that rain down from the upper atmosphere and coat the surface, include some of the same compounds involved in prebiotic chemistry on early Earth. Dragonfly will land in the middle of it and start measuring. If the chemistry in certain locations has moved further along the prebiotic pathway than it should have on its own, that is something worth paying very close attention to. Beyond these missions, there are proposals that are further out and considerably more ambitious. Engineers have drawn up concepts for a lander that would set down on Europa's ice, melt its way through using a nuclear heat source, and deploy something like a small submarine into the ocean below. The ice is potentially miles thick. The melting process alone could take years. Nothing like this has ever been attempted, and it is probably decades away from being technically and financially feasible. But the concept exists. The engineering problems are being studied. At some point, the question of what is in Europa's ocean will be important enough that the answer will be worth that kind of effort. The philosophical weight of what these missions might find is not easy to overstate. If Europa Clipper detects something in a plume sample that biological chemistry can explain and abiotic chemistry cannot, or if Dragonfly finds organic structures in Titan's sediment that look less like random synthesis and more like selection, the implication runs in one direction. Life that arose twice in the same solar system almost certainly arose everywhere conditions allow. The universe contains hundreds of billions of galaxies, each with hundreds of billions of stars, an enormous fraction of them with moons in environments that tidal heating could warm. A second origin of life in our solar system alone would make the cosmos almost certainly full of it. That is the stake sitting underneath these missions. If life exists anywhere else in the solar system, the most likely answer is going to come back from something orbiting a planet, not from the planet itself, and we are going to find out within most people's lifetimes.